So in part one, we noticed that a lot of our acids have hydrogen. Well, is that what makes an acid, that it has hydrogen? Is that the definition? Has that always been the case? The next few slides are going to look at some different definitions over time of acids and bases and how that definition has been refined, and it's not always the same depending on who you talk to. So the first definition of an acid we want to look at is by a guy named Lavoisier. Now look at this date. He came up with this in 1778. Okay, what's happening in the US? Well, just 2 years before we'd signed the Declaration of Independence. We're still in a fight for our freedom here. So Lavoisier, I believe he's a French scientist, and he was really involved with combustion, with burning things. And when you burn things, you have to have oxygen. Well, he found that these compounds that contained oxygen all had these what we would consider to be acidic properties. So he had sulfuric acid, that's what's in car batteries, nitric acid, which is in dynamite, carbonic acid, which is in our current day soft drinks, and boric acid, which is in eye washes. Not saying that they used eye wash at that point in time. But today, these are some of the things he would say were acids because they contained oxygen. This is not a common definition that we would use today, but I did want to point this one out and how that definition is going to change over time. So about 100 years later, we come up with Svante Arrhenius's definition. Now, this is the definition that we most commonly use in chemistry, especially in Chem 1. We'll talk about a couple of other ones that we will see, though. So back in 1887, the story goes that Svante Arrhenius was working on his dissertation so he could get his PhD. Well, he was dealing with conductivity of ionic compounds, and his work did not impress his professors. In fact, they gave him the lowest possible passing grade. But he went on with this same research, did a little more, especially looking at acids versus bases, and he won a Nobel Prize. So keep that in mind. Even if your professors aren't extremely impressed with your research, someone else might be. Now, what Arrhenius's definition is that an acid produces the H plus or the hydronium ion in water. Now, what'll happen once that H plus goes into water, it forms this compound, H3O plus, and we call that hydronium. Hydronium, I should probably spell that out. Hydronium. Now, as chemists, we get lazy. We'll just write it as H+, but if it's in water, it's going to form that H3O+. A base produces OH-, that's hydroxide, in water. Now, this is a really limited definition because, number one, it has to be in water. Number two, you either have to have H+ or OH-. So this is a very limited definition, but it's a very, very useful one. Now down on the bottom is trying to show what happens to ionize your acid. So here they have this little picture. It's of a kid and a man, assuming a child and his father, that's getting ready to jump into a pool. And they're holding hands, and that holding hands is supposed to represent the bond between them. Now once they jump in, they let go. Once they jump in the pool, they're no longer connected to one another. They're two individual ions, in this case H+ and the chloride ion. So acids, when you put them in water, that molecule will break apart and form ions. Now the next definition comes out in 1923, and this one's called the Bronsted-Lowry definition for the two sciences, Bronsted and Lowry, who ended up working on this. Their definition is a little more general. It does not have to be in water. It says that an acid will donate a proton, and for us, a proton, they're going to say that it's an H+. We don't have to worry about the hydronium, but the acid is going to donate an H+. or a proton. Those two terms are sometimes used interchangeably. And a base is something that can accept or take that H+. This one does not have to be in water. So something that I've learned to really appreciate is to look closely at the pictures in your book to be able to try to see what they're trying to say. This one is comparing those two definitions, Arrhenius's definition and the Bronsted-Lowry definition of an acid. So up at the top, we have Arrhenius's definition. It says we're going to start off with HCl, and we're going to put that HCl in water. Now, because HCl is an acid, it's going to break apart. It forms, here's a hydronium, and here's a chloride. Notice there's no HCl left together. It's completely separated. And then we have lots and lots of water molecules. The Bronsted-Lowry is a little bit different. So we still have HCl. But what it's saying is that we take this little hydrogen right here, this little H+, and we give it to ammonia. That ammonia forms ammonium, and we're left with a chloride ion. Notice there's no water. There could be, but there doesn't have to be. Now, the Bronsted-Lowry is a more general definition, and it works really good for the bottom picture. Now, in the bottom picture, they have two bottles. One's ammonia and one's hydrochloric acid. But they don't actually mix them together in a liquid form. What they did is they took off the cap and some of the vapor rose into the air. The vapor mixes and you're left with that white smoke. It's not actually smoke, it's actually ammonium chloride. It's actually a salt that forms when those two gases start to react. So Bronsted-Lowry does not have to be in an aqueous or a water state. Now, there is one more definition that's very common. It's called the Lewis definition. That is named after G.N. Lewis, who is an American professor of chemistry. He is the one that came up with the Lewis structures and the Lewis symbols to be able to draw bonding ideas. He dealt a lot with covalent bonding. His definition deals with electron pairs. It's much more general. You don't have to have hydrogen anywhere in there, but we show how an electron pair can move from one substance to another. Whatever has the electrons is your base, and whatever takes the electrons or accepts the electrons is your acid. This one is used a lot in organic chemistry. I wanted to be sure to mention it, so if you go on to a biochem or a GOB course, you'll have at least heard of this before, but we won't be talking about it in this class. Okay, so here we are back with an acid-base neutralization. If you take your acid, you react it with the base, you end up with salt, and you end up with water. If we were to simplify that equation as much as possible and remove what are called the spectators, based on Arrhenius's definition or the Bronsted-Lowry definition, we'd end up with this. H+, or our proton, reacts with OH minus hydroxide, and it's going to form water, and water is a neutral substance. So here's a quick question to end this section. Hydrogen ions react with chloride ions in acid-base neutralizations. Now, we just talked about this. Do you remember? This would be false. Your hydrogen ions, your H+, react with OH negative with hydroxide in your acid-base neutralization. They're going to make water.